So everybody heard the recording progress thingy? Yeah, all right. So this is done. So what are we gonna do today? Well, okay, this was zero. Let's look again at the proof of QKP because I think it was not really well explained yesterday. I mean, the trick is what I told you. Maybe the constants don't coincide when you are trying to make your L places hanking, but I will try to make it a little more clear today. Then we're going to talk about higher order logic and why it is important, and we're going to use simple type theory for that. And then, if everything goes well, we're going to see this interesting system, which is higher order S5, which is the necessity system of Williamson. So, before I start with that, are there any questions from yesterday? By the way, I do want to ask now, I do have a question. Do you think I'm going too fast? Okay. Also take into account what is the goal with this, right? I'm not even leaving any exercises or anything like that. The idea is that you get a good grasp of what this is so that you can then go and get into the system. But if you think I'm going too fast, that is perfectly okay. All right. So the naive approach, completeness, and then what I had. Oh, I also added a section on why is it more difficult to prove the canonicity for um, canonical constant domain frames. But for the time being, let's go to our. This is going to take a while to. Oh no, we done it very quick. That's good. Mm. I just got this tablet, so I'm not familiar with the. It's my first time using Apple, so this is going to take a while. Sorry. No, this is not how I do that. All right. You're keeping the outline then. All right. So what we were looking at yesterday was how it is easy to construct the canonical models for logics that have forward-looking axioms, right? And those are the axioms that tell you there is a successor, there is an endpoint, there is a next one if you are connected via two, if you are connected to another one that is connected to a third one, you get the other one for free, etc. And the problem was looking backward. And for that, we had this axiom, and the axiom is symmetry. And symmetry, remember, if you uh, if you haven't seen it in a while, this is symmetry. So if something is true in that world, then it is necessary that it is possible. And that basically means that for any world it can see, that world can look back. So the failure is going to occur when two worlds disagree on which constant witness an existential fact. So let's consider the following scenario. So suppose we have gamma that contains this existential claim. And since gamma is an L place, it is hanking complete, so it has a witness for that. Good. What is the witness? C. And we have it such that PC is in gamma. Now suppose that gamma also proves the verum, which means that it's not an that it can look to other worlds. So we construct a successor world delta such that this is the case. What does this exactly mean? Remember that we have this canonical relation that it basically says all my necessities are true in me for you. And then this is a forward construction that ensures that what I just told you, that if necessary in gamma, then unboxed is in delta. And the conflict comes when you say that it is logically consistent with all that we have said, that we have a formula that it is necessary P of D. Can you see where I'm highlighting? No. What the hell is wrong? Okay, this. But at the same time, we have that these two are different. And since there are different syntactic objects and they are rigid designators, so we can conclude that saying that D has P and that C has P, these are distinct formulas. Now, to satisfy symmetry, we need this too. But take into account that this is a necessary statement. So it means that PD needs to be true in gamma. So this requires so we must have P and D gamma. But gamma does not contain D. It contains C. And let's suppose that C is the only object in the domain that has P. Because the canonical model treats constants and rigid designators, the interpretation is going to be the object itself. So the fact that C satisfies P in gamma does not help satisfying the requirements that D must satisfy P. Thus, this condition fails because we cannot establish this. So the idea is that this is now more clear. Sorry that yesterday was a little bit convoluted. I hope that this is clearer now. I stayed yesterday doing this, so I hope it's better. But if not, please do tell me, and I'll try to improve it from there. All right. I have some. Okay, we have done this. I need to ask you for offer you some apologies because sometimes I've confused the Barkan and the converse Barkan formulas in the way I write them, and that this had happened both how I write them here in the Blackboard, let's say, and how it's in the notes. In the notes, I'm in the process of putting everything uniformly, but so that we are clear. So converse Barkan formula is box for all x. Let's do it with phi. Then for all x, box phi. And the Barkan formula is for all x, box for all x phi. Where has the confusion lied? And this is entirely with where the boxes were put. Sometimes I was saying, yeah, and this satisfies the converse Barkan, but I really meant the Barkan. So, if anything, take into account the formulas that I've written, not the names that I've given them. This is the standard, and this is how it's done. Sorry. All right. I want to ask you now, because now we're going to move, if someone has already is familiar or has heard of Williamson's work on modal logic, especially in this higher order. I know that Andrea has. I don't know how excited he is for it because it can be. Yeah, Andrea is excited for it. That's very cool. But is someone else familiar with it? Sorry, I was looking at the screen, but no idea. All right. So what is novel about this approach, it is that Williamson is a philosopher. He's also a, let's call it a logician to say so, but he's a philosophical logician. But he's really good at maths. He studies maths also. So when he says something and he comes out with something that is maybe unintuitive from a philosophical point of view, people normally take it seriously because he's also a very great logician. This is because what I'm going to introduce are some dubious concepts, tools, etc. And the first one that we're going to talk about today is the idea of higher order logic. Has someone has a here I'm sure has heard of higher order logic, but can I see a show of hands if you have? If you have ever encountered? Have you Jan, was that a hand? Or okay, yeah, good. So what is higher order logic? So the idea, oh, Magnus has heard, oh, great. The idea of higher order logic is that higher or second order logic and higher order logic. The idea is that we amplify our way of referring and quantifying over things. So, well, first order logic restricts quantifications to individuals. Then we're going, a second order logic is quantification over properties. In more mathematical terms, this means that we are quantifying over elements of the domain. And here we're quantifying over subsets of the domain. So this has a very interesting story in the history of modern logic. Unfortunately, we cannot talk about it today, but right now, today, the easiest way to get into second and higher order logic is by means of simple type theory. That I know that in the more simple type theory is taught in the type theory class, of course, and also in proof theory. So maybe my presentation is going to vary a little bit from what you've seen, but I hope that there's not a lot of mismatch. So the idea is that we have a set of types, which we're going to denote as T, and we are going to define it recursively. So the first thing is that E is a type, which is going to represent our type of entities or individuals. Now we're going to have another type, which is the type lowercase t. So it's a type which is going to represent the type of truth values. Magnus, you're here twice. Great. Oh, no, just once. Now, and then our recursive clause is that if alpha, so if alpha and beta are types, then alpha 2 beta. This I know I'm using the same symbol as in the conditional, but I hope it's not ambiguous. But the idea is that you say this as 2 is a type. And intuitively, this is the type of functions from alpha to beta. So there's other ways of writing this. So you can lose the parenthesis. Sometimes it's not ambiguous, but sometimes it is. And sometimes people write it like this. I think Ed Salta likes to write it like this. You can choose whatever you want. But for instance, what I want to tell you is that if we have an object of the domain, so let's say say D is in the domain, then where we're going to start is we're going to type the expressions. So we're going to say that D is of type E. If you are into type theory, people normally use this notation. But this creates some readability problems if we are not using a sequence calculus for this. So let's stick with small. So, but let's say that, yeah, so unary predicates, let's say this is P and this is unary. So we're going to say that P is of type E to T. And the intuition behind this is that it is something that is expecting an object so they can give you a truth value. So a predicate, normally it's, if you look at it like this, if you interpret it as a computer program, it's basically a computer program that is expecting an input. And once you give it that input of type E, and once you give it, let's say our D, then this is going to be true or false. Now, we can do something similar if you want for binary predicates. Let's say that P2. So this will have type E to E to T. Oh, this is horrible. All right. So this is saying that I am expecting two inputs. I'm going to put them like this. I need to give you one. Let's say I fill it up with D, and then I'm expecting another one of type E. And once I get it, then I get something that it is true or false. All right? Questions about simple type theory? All right. So the idea of this, this is not going to be useful today, but if you go into the Williamson stuff, well, the things I'm going to say right now are going to be very useful. And the idea is first, so some facts about this. So for every type A, you need to add a set of variables. But of course, you're going to have to denote it in a very cumbersome way, which is, let's say that phi is a variable. So you're going to have that this is a variable of type A with letter alpha, I guess. Alpha, and then you're going to have to give it an assignment. So for instance, we will have alpha 1, that this is the second one, etc. Or you can use different letters, whatever you want. Now, on the other hand, we're going to have something called lambda abstraction and application. So the idea I told, this brings us very close to this interpretation of this as computer programs, but basically what I want to say is that if phi is a term of type beta and x is a variable of type alpha, then we represent this as, so we can abstract away the alpha by saying lambda x of alpha is a term of type alpha to beta. And the idea of this is that you do the opposite of what I was showing you here. So if you have something, so this is going to be of type T, but if you have something of type T and you go the other way around and no, but now I have variables, so I can use it before I didn't. This is basically going to say that I have an expression which is of type E to T. And then the other thing that we can do is what I was explaining you before, but now let's do it more formally, which is called application. An application says that if lambda, sorry, if phi is of type alpha to beta and psi is of type alpha, then the application of psi to phi is of type beta, which is what I explained you before. Now, with this in mind, you're going to understand a lot of things in proof theory, I hope. But if you take the Williamson path, then this is going to be useful again. So let me see how we're doing. Oh yeah. So there is another thing that I wanted to show you with this, and it is the fact that now you can define predicates in a very interesting way, and you can define it for all the types in the language. And for that, I'm going to introduce the idea of identity as a definition. So the idea of people that work in metaphysics and in philosophy of why using higher order logic is the ability to use identity, sorry, to define identity rather than taking it as a primitive. So one of the things that you normally do in first order logic is that you introduce a symbol which is primitive, and you call it identity. Or you can introduce it as a non-logical symbol and you give it a fixed interpretation. Whatever you do, you can never just take it and define it. But Ludovico brought something very interesting to when we're doing the bingo, and it is the fact that there is Leibniz law for identity. Can you, Ludovico, will you mind sharing what's Leibniz law in terms of identity?
Well, if two objects have the same properties, then they are identical, right?
Okay. Yeah, so if for all x, p of x, if and only if p of y, would this be a fair reconstruction of what you just said?
Yeah, exactly.
Yeah.
Thank you.
But notice that here we are quantifying over predicates. So we cannot do this in first order logic, right? But now that we're in higher order logic, we can do this. Why? Because we can understand quantification of this and quantification of this as quantification over different types. So we can make something like an identity for all the entities. So we can define, so how do I call them here? Individuals. As simply X is identical at the level of objects to Y if and only if for all all the properties that are a type higher, they share them. So notice something very important, and that so this here and this here are different, but are different only with respect to two symbols. And that is, this one is of type E to T, meaning that all the predicates that can be, that are there for E. And this one we have just entities. You can generalize this, and there's people that defend this kind of thing, and you say that for any arbitrary time, you can define identity for any arbitrary type as long as you keep the type distinctions strict. And there are some other people that says that they make, oh, sorry, this is bad. No, this is better. There are some people that have defended that you don't need it this strict, so you can the only requirement is that it's higher than the original, but in this we're not going to discuss about this. Any questions about type theory and how we do this kind of weird things with the language that we now have? All right. So let's start talking about higher order modal logic. So we're going to talk about basically the work of one guy, which is Timothy Williamson, and his book, which is called Modal Logic as Metaphysics. What is defended on this book is that quantified, higher order necessitist S5 is the correct logic to talk about metaphysics. So this is the correct system to talk about our intuitions about possible objects, counterfactual objects, things that may come into being, things that stop being, and basically what he's going to give us is, in terms of what we have talked so far, is that the naive approach is not merely it's convenient mathematically, but it is the correct metaphysical theory in view of necessitism. So what is necessitism? So remember that necessitism, it means that necessarily, everything is necessarily something. And Williamson says the way of formalizing this is for all x, so box for all x, box there is a y, such that this is the case. So this is the thesis that he defends during the whole book. And he also defends the fact that no other interpretation of quantified modal logic can do better than necessitist S5. So if we unpack for a second that in terms of what we know so far, when we say, if I tell you that this is a necessitist position, this should tell you something about what this means and about what this means. So about the quantifiers, it should tell you that we're talking about fixed domains. And if I ask you what is this telling us about the modalities, is that this is going to satisfy the Barkan and converse Barkan. All right. So for the language, we're going to use the types that we just defined, and the language. Yeah, so definition. So, and the language that we have for higher order modal logic is going to be determined by a set of variables, and we're going to have a countable set of variables for each type. We're going to have our constants for each type. We're going to have our logical symbols. We're going to have application, and we're going to have abstraction, as we have just defined them. And in terms of the semantics, things are going to change a little bit. So we're going with a fixed domain this time. And the crucial feature is that domains for higher types are also fixed across worlds. So remember what I told you about the naive approach, that you can make this idea that you can assign different valuations in each world. That was the way of doing it. Here, things are going to change a little bit, and let me show you how. So, we're going to define a frame, and we're going to define it. Oh, yeah, so fancy F, worlds, accessibility, and a domain. Worlds is what you expect. R is going to be from the get-go S5. And D is going to be a hierarchy of domains for small t and big T, defined as follows. So we're going to have DE, which is non-empty, sets of individuals of individuals. We're going to have a domain of truth values, which is simply going to be C11, because we have basic, these are the two basic types. So you can interpret this as functions from W to, and then you're going to have a domain alpha to beta, which is the set of all functions from a domain alpha to a domain beta. Are we good with this? Do we vibe with types? Great. So before we jump to the defense of necessitism, let me just briefly tell you that we are not going to see a completeness result today. What we're going to see is a kind of argument that Williamson gives, so that he creates a defense of this system with respect to some other meta theoretical result. He's not going to tell you this system that I'm going to give you is sound and complete with respect to this set of action, but it's going to be sound and complete with respect to something that we will see later that is called metaphysical universality. I'm gonna leave it there for just now, and then we will come back at 5 past to start discussing all this about metaphysical universality. I hope that's okay. So if you don't have questions, I'll see you in 10. All right, so let me ask very quickly if anyone has questions about what we just discussed. Right, so things are only going to get weirder from now on because did I define identity? No. So yeah, so um, now that we have this higher order system, now we're going to see how it makes it the necessitist and how it validates the necessitist claims that Williamson meets. So I'm going to go over a long argument that he has, and part of the task for the people that want to take this system is go a little bit more in detail of how this argument works. Again, we're not going to study a proof, but more or less an argument that is given here. For the claim that quantified is 5 with fixed domains and is the correct modal logic to talk about objects, um, to talk about metaphysical reality. So the idea of this is that we first remember the how we formalize necessitism. And we said that for Williamson, it is the claim that necessary for all x, necessarily there's a y such that x equals to y. This basically means that in every possible world, everything is going to be identical to something. This, if you want to model it very simply, uh, I'm going to ignore all the arrows that follow from this. So this is transitive, this is reflexive, everything that you want is there. This is an identity equivalence relation. And basically what we're going to have here is that for all objects, so the domain is going to have some objects. So yeah, let's use C, the vector, just in case. So we're going to have C1, C2, and C3. But the idea of this is that we say that necessarily for all x, and then we say, okay, so everything here, that means nothing is left outside. There is something in every possible world such that that thing is the first thing, it's the second thing. This basically means that you're going to find those same objects all around the domain. So, by the way, yeah, just in case, this is the the basic way of putting this is that like this. But also, you can have it for an arbitrary type. Williamson has it, so it's very interesting. Well, what does this tells us? So Williamson says, well, if this is correct, then it has to be the case. From this, it should follow our good friend, the Barkan formula. Because this basically implies, so not only so not only the Barkan formula, but the converse also does. Because if we have this and we combine it with the fact that the domain is fixed and it has to be populated across all worlds in the same manner, this means that the domains are constant. So the converse Barkan formula tells us that domains are nested. So you can only add, so in the next world, which is accessible, you at least have to have any objects that you, so if W1 is accessible to W2, then the domain in W1 is included in the domain of W2. Of course, we have not defined this in any sort of way for this system, but think about it in the sense that there is think if there was a domain for world one, it would have to be included here. And the Barkan formula is going to tell us that domains don't shrink. Which is basically that if you have something in the domain and another world is accessible, you don't lose any of the objects that you had before. So you cannot take, it's not only that they have to be the same, you cannot remove anything from it. So the other one is telling that you cannot add it, the other one is telling that you cannot remove from it. Now, this raises a question of how we define identity, and then this is going to be very interesting for how you feel the bingo for this one, because then we're going to define Leibnizian identity as follows. So we have two terms, x and y of type T, and then identity is going to be defined as sharing all the properties, so of type small t. I should have not used t here. So in the notes, I use a tau, which is better for this. But let's say A, and then identity is going to be defined in terms of properties of type A to T. So it is what we had been seeing before when we discussed a little bit identity in higher order logic. So two things are identical, we define it as they share the same properties. Alpha to T, P of X, if and only if P of Y. So this is going to lead us into a problem if we interpret this in a very strict mathematical sense. Because this says that you can also have identity of properties, you can also have the identity of properties, and so on. And Williamson is also wants to have this. Which is the necessity of identity. And then there's an even stronger version of this, which is here, but we're not going to concern about this version right now. But the point of this is that you understand that if you, for Williamson, if you define identity like this, And if you have necessitism and you have Barkan and converse Barkan, then you obtain this for free. So identity is going to be necessary. And this is very important for him because this is one of the central theorems of the first systems of quantified modal logic, those of Barkan that I mentioned yesterday. Magnus, please.
Yeah, I'm wondering, is like depending on how you see it, is this formula even, get me right, saying anything? Because like usually when we're talking first order statements, we're counting forms of x equals x, like things equal to itself in the
Yeah.
realm of tautologies. And
Yes.
like usually when we're doing modal logic, like usually require that tautologies be true everywhere. So
Yeah.
it's saying like something implies box something. Like it's like so
Sorry.
if the antecedent is true, then if x is equal to y, then
Yes.
x equal to y is always true.
Yes, so that's the
Yeah,
point. So in
right.
every possible world, it's going to be the case that those two things are the same. So if you
Okay.
can, so if you, but what does that exactly means? It means this. So it means that
Yeah.
it two things share the same properties in one possible world, then they're going to share them in all possible worlds.
Okay.
Better? All right. Now, this is problematic for some people because in traditional, let's call so first order logic is sound, complete, and compact. In second order logic, there are ways and ways of doing this. There's something on the notes about this, but depending on how you do it, if you accept that your domain, the domain of quantification, it's sorry, your first order variables can range over the entire power set of the domain. This is called the full semantics. Then this is sound. This is not complete. And this is not compact. And it basically has to do with how much things you can say in um, second order logic, but it's basically if you want to do one line argument, this can perfectly encode arithmetic. I by Gödel's incompleteness theorem. This should be incomplete. Um, and then we have general semantics, which were created by someone that has been name dropped a lot here, which was Leon Henkin. So Leon Henkin proposed a way of restricting your subset, the subsets that you can quantify over, to make it a little bit more manageable. An example of this, if you take only monadic second order logic. Monadic second logic is sound, complete, and compact. But so it depends a lot of how you do it, but in general, it's going to be sound, it's going to be complete, and again, also in some cases, it's going to be compact. Now, when it comes to how we're doing things, so when it comes with how Williamson does things, this should be very important for us because then you should be asking, wait, you're just giving me a system, but it is going to be he hasn't made any restrictions about the domain. Hasn't done any restrictions about this hierarchy of domains. So it should be very obvious that this is going to be not complete. Maybe it's sound, which would come as a nice thing, but we should have a way of making this complete so there are not unprovable truths to say. And then what Williamson does, and this is where maybe for the mathematicians in the audience, it becomes a little bit more confusing, is to reject something that he calls pure model theory. So in the previous sections, we defined soundness and completeness relative to a class of frames. So for instance, for quantified S5, we said that it's complete with respect to the equivalence frames or Euclidean frames. And Williamson is going to reject modal theoretic methodology to say that this should hold what model theory tells us should hold also for our metaphysical logic that we're constructing. So when it comes to model theory, so he says, quote unquote, it does not engage with modal reality. And then why is this important? Because he has a logic which has the necessity of identity, the converse and the Barkan and the converse Barkan formula has QS5, and then and second order logic, this is a recipe for disaster from a mathematical point of view. But then he makes a very a very interesting argument for the following thing, and he uses the physical universality, no, the necessity, no. Yeah. So I'm gonna read from Modal Logic is Metaphysics because I think this passage is very interesting. So please follow with me. Since what matters is only the structure of the inhabited frames, not the nature of their constituents, some countermodals of Barkan formula and the converse Barkan formula have variable domains whose members are all numbers or pure sets. We did not check whether those entities really have contingent being because that question is quite irrelevant to whether the model falsifies Barkan formula and the converse Barkan formula. We should not expect variable domains model theory by itself to explain why the two formulas fail, nor should we expect constant domain model theory by itself to explain why Barkan and converse Barkan hold. And then I have this thus proving that a logic is consistent with some class of pre-frames does not settle the metaphysical question of which is the correct logic for metaphysical questions. We need a criterion for truth that targets what he calls the intended interpretations. And the problem, as I'm putting it here, is that model theory, standard model theory is neutral. So it's about models that have either pure sets or numbers in them, but it is not really useful to think about objects in our reality and do modal reasoning with them. So what Williamson is going to argue is that, well, this kind of model theory, which allows us to construct models where the Barkan formula fails, and sometimes where it holds, but as metaphysicians, if you're jumping the metaphysics bus with him, should not care whether or not Barkan fails for numbers or arbitrary sets. What we care for if it fails for the actual objects that make up reality. And for that reason, he's going to depart from traditional model theory and he's going to talk about something called the inhabited the intended inhabited model structure. And it's going to have a really interesting thing with respect to all those models that we have studied. So we're going to we can abbreviate it like this, IIMS, and we can represent it with the fancy, I've never known if this is a G or an S. Well, this is one of those fracture letters. And then let's. So what? G. It's a G. That's great. So what is new with this? You're going to notice that we have a new player in town, and there are various ways of coding exactly what I'm going to tell you right now. And it is the fact that this is a so-called pointed model. And in this context, it means simply that we're going to have a special possible world. And that special possible world is going to work like this. So W is going to not be the set of all possible worlds, but the set of all genuine, however you pronounce that, metaphysical possibilities. So what we take as possible worlds are not just points in a model, in a frame, but we're going to interpret as metaphysical objects in their own manner, like possible worlds. What is a possible world? In this sense, well, it is difficult to explain it right now, but it is ways in which the actual world could have been. So we're not interested basically in a bunch of mathematical problems about frames, about how the worlds connect with each other. The idea is that if we interpret this as possible worlds in the sense, in a strong metaphysical sense, then we're going to not only have a very good idea of how these worlds communicate, but we're also going to make room for a very special guy who is the actual world. There are ways of um, coding this or representing this differently, but basically this is a, yeah, an element of W, which is supposed to represent this present reality, the one in which we are sharing right now. So there could have been a possible world where the flight to Amsterdam of Isabella was not canceled and she was here with us today, but that is not this possible world today. But that tells you that if there is a possible world in which Isabella was here, we can also from that possible world say, hey, Isabel arrived. Is there a possible world in which this was canceled? Yeah, and it is a pretty close possible world with all these cancellations that are happening right now. But with that, again, we have this relation, which is metaphysical accessibility. And Williamson, for a second, is going to tell us, let's not look at it very much. We're going to have to derive how this works. But basically, at the end of the line, we're going to find, again, S5. So spoiler alert. And then for D, it's going to come very weird for some of you, but it is the domain of everything that is. And since we are in very philosophical, metaphysical terms talking about this, let me tell you about everything. It is absolutely everything. It is not everything that exists, everything that could possibly exist right now, every thought that you had, every weird idea, every feeling that you had, all of that is there. There are models that you can make different models of this, and this is a very weird system to work with because we are not going to have something like an interpretation function because interpretation functions are going to be in the domain. So we will have to look for a fancy way of defining this. It is super interesting stuff. I'm not going to highlight how to or explain how to it's. But what about Russell's paradox? Yeah, that's a great one. But the point is that no, you cannot put the domain in itself, so you don't have so you only have one, so you cannot put the Russell set there. You can put maybe your idea of the Russell set there. So this behaves classically, let's say. But if you're interested, there is the 2003 paper which is called Everything by Williamson. And it is fascinating because if you read the first 3 pages and if you read if you read the last 3 pages, that is everything that you need from it. And this is because he's going to give example after example of what everything means. And then in the last 3 pages, he explains how the logic works. And it is this thing about how the interpretation function has to be different. So since you put everything in the domain already, how do you work with the logic of that? And he has some formal logic um, background for this. So he has also worked with logics with infinitary domains. So don't worry, this is covered. This is not just some philosophical nonsense. It is actually like a well thought philosophical thesis. Unfortunately, we cannot go a lot into it, but let me know if you're interested, and then maybe we can, like have a coffee and discuss everything. All right. So when we do this, we come into a place in which this is radically different from everything we have seen, right? Because I told you, oh no, this is domains, and you just have objects, and in the domain you have objects, and then those objects, you interpret them according to a function, and then you map them to a possible world, etc. Here, we're talking about the metaphysical real world. If you are a skeptic about if the world exists or not, if this is a simulation, or maybe this is not your cup of tea, I guess. But with that being said, the idea is to focus in if we have the intended inhabited model structure, this should tell you right now what facts are we interested in. So the idea of this is that not that this is able to establish contingent facts. So MS is not going to talk about contingent facts. What we want in our logic is to prove general laws. This is what we are concerned with. So what are those general laws? Difficult to say, but Williamson has a sort of answer for that, and it is basically that is able to prove everything that is metaphysically universal. What is metaphysically universal? Is everything that you can prove in another system, which is called second order propositional modal logic. So for this, let me make a small footnote here, because here I am uploading some of the technical details that we need, and I'm going to skip over this a little bit, but just so that you know, this is a system which is a bit stronger than S5, and is the system that you obtain if you add quantifiers directly to modal logic without adding first order entities. So this is a system of propositional quantification. So the idea of it is that you have your variables and you have the modality and the quantifier, and you can say stuff like this. So this says that everything necessary is true, and the other one says that there is a contingent proposition. With this, you can derive, you can have a semantics, which is basically, so you have your frames, and then you will have a model in which the domain is the set of proposition and it is fixed and it's rich semantics. With this, you should be able to prove the Barkin formula for propositions and so on. But at the same time, what we are concerned with at this stage is the fact that we are able to prove the first order counterpart of this in the intended inhabited model structure. So the idea is that the proof is going to work differently because we are not going for soundness and completeness, but we are going for soundness and completeness with respect to metaphysical universality. So what is this thing about metaphysical universality? And we're going to say that a formula phi is metaphysically universal if and only if it is true in the intended, inhabited model structure under every assignment of values. Okay, so it's non-logical predicates. So the idea of this is that, roughly speaking, a formula is metaphysically universal if it describes a structural feature of reality that does not depend on the nature of the properties involved. So, for instance, what is something that should be metaphysically universal? For all x, if p of x, then p of x. They should be metaphysical universal because it should be irrespective of how you assign meaning to those predicates, it should hold. And then what also should be metaphysically universal? Well, since we have fixed domains, and since you ask so nicely, the bargain formula should be also universal. Even though we can mathematically create models where this fails, it should be the case that this is metaphysically universal, so we are only looking at things that from our reality should behave as a metaphysical universal formula. So what we are doing right now is not going for our classical soundness and completeness theorem, but when it comes to completeness, what we're going for is to show that every metaphysical universal formula is a theorem. So the inhabited intended model structure, what it's going to give you is a bunch of truths, right? And some of them, what we want to is to map which are the ones that are metaphysically universal, and we do that by looking at the second order propositional model logic. Once we have that, what we just need to prove is that every one of those is a theorem. Now, this is wildly different to what I've been doing so far, not only because the goal that we have in mind, but the way we do it. Because this is not going to work as a Hankin construction or the Hankin construction we are familiar with. But the idea is that we give an argument to this. And again, in philosophy, this is common. You defend the logical system in base of arguments, nor in terms of its mathematical rigor. But I'm going to reconstruct Williamson's argument, more or less, of why a system that makes this kinds of formulas as metaphysically universal is the one that is the best. So, if you're interested, this is called an abductive argument, but you don't need to need that. You don't need that to understand what I'm going to say. So, the arguments that he used for this are, let's say I have three, but he may have used more. I'm not sure. This is the ones that the book is hard to read, and these ones I think are the most important. So the abduction or the methodological argument that he gives is that metaphysics should follow the methodology of the natural science, and this means follow natural science. And this means that we should always choose the theories which are the simplest, the strongest, and most explanatory. What does this mean very quickly? If it is something is simple, it needs very little resources to do what it's supposed to do. If the strongest, in this sense, it can do the most. And the most explanatory is that it's able, what Williamson thinks all these are, is that it is able to explain the phenomena in the best way possible. And here we're concerning the interplay between quantifiers and modalities. So there's that. So when it comes to strongest, well, it's S5. Is there a strongest logic of modality of necessity than S5? No. After S5, you get the trivial logic, right? So that is a good argument for QS5. It is the most explanatory. He gives a long, very long-winded argument for that. I would not touch it here. But what I want to talk about here, which is important for the whole project, is his argument of simplicity. Because he says that quantified S5, it is mathematically elegant, computationally well understood, and structurally simple. So as we saw yesterday, there were some problems with quantified S5 itself. There's not a completeness proof from the canonicity argument. It doesn't mean that it's incomplete. It is complete. But the point here is that if we assume, as many philosophers do, that S5 is the logic of metaphysical necessity, then why do we need to change what we already know? If S5 is the logic of metaphysical necessity, if we go to the quantified version of it should remain so. It is, yeah, it is, and even simpler than variant domains. And we're going to look at that tomorrow a little bit. But the idea is that you see that fixed domains are way easier to work with than variant domains. And he then goes and says, and this is our little look into the future, that if you go and look at the rivals of this, the rival is going to be basically contingentism. And if you want the one-line explanation of contingentism, is this one. Simply negates. So not everything necessarily is something. This requires that we make a distinction between existence at a W and something more ethereal. It could be, some people call it subsistence. Some I think it was Minon who called it subsistence, then Mali used other word for it. But the idea of this is that you break apart how you do quantified logic. And then you give me the quantified modal version of that. And what is the most popular way of doing this? Is by way of free logic. And this is what we're going to see tomorrow with the rest of. I'm not finishing the class, by the way. I still need like 5 more minutes. But this is what we're going to see tomorrow about free logic. But Williamson thinks that free logic is more complex than the constant domain modal logic, which is, yeah, he's right. We will see that. But and it has restrictions on inference rules. And to give you a first taste of that, of how this works, normally what we have in uh, in quantified logic is that if we know, if we show that for an arbitrary A, an arbitrary Y, I'm going to write this again. Sorry, I'm being sloppy. I need to. Normally, it works like if you have an arbitrary Y for which you've shown that, let's put the sigma here, then you can conclude that all X contain that. This is the traditional thing. But now what we need to do, if we go to free logic, is to add a restriction. And that restriction, the most popular one, is to add a predicate, a special predicate, which is going to be existence. And since in our domains we can give different interpretations to the predicates according to worlds, that means that we can make existence in worlds different. So we can have worlds where these certain objects exist, but some in which some other objects don't exist. So if you compare the previous one, which didn't have this part here, this is the new part, then yeah, you say, yeah, the other one is simpler, right? I mean, the inference rules are simpler. But we're going to see that we can maybe capture even more intuitively our thoughts about the possible daughter that my possible daughter or my possible fourth no third brother and stuff like that with this system. Because if you think about it, what Williamson is selling to us, if we put it like very naively and we're a little bit unfair or non-caritative with the interpretation of this. This is basically telling us that all objects across possible worlds are the same. What they change are their properties. So, sorry, are the same. So you are going to find all the objects in all possible worlds. But it means that we all exist here, and in all possible worlds, you also exist. But it may be not the case that you are uh, a human, that you are a a student of the mall, etc. But you are other things. The straw man way of putting it is like, yeah, there's worlds where I am a penguin, but or there's worlds where I am I am a table. There will worlds where, but etc. But the this is like straw man in the thing. Remember that we care about metaphysical universality, not this like little funny arguments that we can make with it. But yeah, so necessitysm is committed to this, but this is the like the clown way of reconstructing it. Now, there's another argument that I want to touch, which is the argument for expressive power. And the argument from expressive power is basically going to target everyone who is a contingentist and has a contingent logic, and is going to say this uh, this problem of empty names. Because here what happens is that empty names, as I was telling you during the bingo, are names for which there's no reference in this possible world. So the idea is that maybe there's no reference. So necessitism breaks down this, and please take this into account when you fill up the bingo, breaks this down by saying that everything is something. So Sherlock Holmes in this world, again, the naive and clowning way of putting it, is something. Sherlock Holmes is out there, right? But what happens is that there's another possible world, metaphysically possible world, in which he is a detective. But the point of contingentist logic is, as I told you, is to break this being into various layers. And the point is that if you take Sherlock Holmes and you evaluate Sherlock Holmes, so there's not going to be this is the antiset. There's not going to be a referent from it. So it is very weird and difficult to evaluate a proposition that such that it is possible that there is an X such there is Sherlock Holmes because you don't have anything in this world which is Sherlock Holmes, but then you're telling me that possibly there's something else in the metaphysical possible worlds which is it, even though you don't have anything right now. But the necessitist again like has a point here. And the last thing that I want to say, and yeah, this is where we're going to talk tomorrow about this, and it's the fact that we can deal with identity pretty simply. We define it, and we have it for every type. And this is basically a challenge of Williamson to other people out there. Say, I challenge you to come with a notion of identity, which works across possible worlds, and it is contingent. So that you can have contingent identity, because he said like if something is identical, that is necessarily so. So I can fix I fix the problem on it. The problem fixes on its own. But if you do not agree with this, then you have to explain me this idea of contingent identity. And well, that's about it. That's everything I had for you today. I hope you have enjoyed this philosophical excursus. But at the same time, I want to open the floor for questions. All right. If not,
Question,
yeah.
because I on the website for the course I couldn't open the second lecture.
Yes, and now I fixed that just
Oh,
before
okay. Great.
yeah. And the third one should be uploaded shortly. But yeah.
Okay, great.
But thank you for raising that issue. Tom told me also. All right. Well, if I think that's about it. I think I'll see you tomorrow. Thank you for attending once again, and have a nice day.